We're going to study gases, and of all the phases molecules can have, gases are probably the easiest to model. Gases are relatively easy to model because they don't have strong interactions with other molecules. In fact, in the gas phase, this is where their interactions with other molecules are the weakest. As you know, gases are highly compressible. It's very easy to take something like a bicycle pump and transfer air from the pump into a tire by actually compressing the air inside the bicycle pump and forcing it into the tire. Gases also have low densities relative to the other phases, solids and liquids. Gas molecules are free to move around. Like the animation shows behind me, molecules are unconstrained. They can move wherever they want. And we'll talk about those motions molecules can have in a subsequent section of the chapter. Gases also happen to form homogeneous mixtures. When we combine two or more gases in some sort of enclosed vessel, the gases disperse themselves evenly throughout that container. Now, when we talk about gases, we often refer to pressure. Pressure is simply a force that is applied over some area which we define. Atmospheric pressure, for example, is the force or the mass of all the air above us that is pushing down on us. At sea level, the pressure is often referred to as 1 atmosphere. However, there are several versions of pressure out there. There's no one unique one that is exclusive to all science, although there is only one that the SI system officially recognizes. All right. So when we have pressure and we talk about different measurements of pressure, the most common is the atmosphere. The atmosphere is, again, the force, or the pressure, I should say, that you feel at sea level. As we climb up the mountain, the atmospheric pressure decreases because there's not as much air pushing down on us at higher levels compared to sea levels. On the other hand, if you go to someplace like the Dead Sea, which is actually below sea level, then when the pressure that's exerted on you is actually increased. It's slightly above 1 atmosphere. Another unit we have for pressure is torr, or millimeters of mercury. And yet a third type of pressure measurement we have is the Pascal, typically seen as kilopascals or megapascals. It just is a matter of how sensitive the pressure measurement you are using is to convey the significance of that pressure. Now, when we talk about pressures, in chemistry, we talk about gases having a standard temperature and pressure. This only applies for gases. Most other chemistry, there's no such thing as a standard temperature. But when we talk about gases, we can refer to standard temperature and pressure as being 1 atmosphere pressure and at 0 degrees Celsius. Now, you may look at the units and say, well, torr and millimeter of mercury, that's kind of a weird system to measure pressure at. And it is actually one of the earliest ways we could use to measure gas pressures. In fact, an Italian scientist by the name of Torricelli developed the first barometer when he was trying to measure how fluids actually leak out of systems. But the barometer is simply a device in which a fluid fills an evacuated cylinder, and it's the atmosphere itself that is pushing that fluid up the evacuated cylinder. Torricelli chose mercury to fill the cylinders because of its high density. Mercury liquid is 14 times more dense than water. And as a result, when mercury is pushed up into an evacuated column at sea level, it actually has a height of 760 millimeters above the base level of the mercury fluid. Later on, in order to honor Torricelli, they changed millimeters of mercury to the torr. After that, we got to something a little more simplistic, such as the atmosphere, just because it's really just a matter of convenience to say if you're at sea level, you feel 1 atmosphere of pressure, rather than trying to remember how many millimeters of mercury you have present.